Hey everyone, and welcome to today's Explainer. I am absolutely thrilled to have you here right now because, well, today we're going to do one of my absolute favorite things. We're taking something that looks super complicated, something that usually requires a ton of rote memorization, and we are going to completely demystify it. So let's just dive straight in, shall we? Today is all about coordinate geometry. And this is the exact same logic your phone's GPS uses to pinpoint that nearest coffee shop, or how video games calculate boundaries to render those massive, real-time 3D environments. If you've ever stared at a massive clunky algebraic formula and thought, where on earth did somebody even get this? Well, you're in the right place, because we aren't just going to accept the math today, we're going to derive the whole thing, step by step, together.
So here is the core mystery we really need to solve today. How do we find the exact distance between two completely abstract points on a graph? I mean, think about it. You've got a Cartesian plane, you've got dots just kind of floating in space. How do you actually measure the gap between them when you don't have a physical ruler? We need a universal rule here. We need a formula. But instead of me just handing that formula over to you, we are going to build it from scratch.
Section 1. The distance problem. Okay, picture your standard Cartesian plane. Your classic x and y axes. Now let's drop two distinct points right onto that plane. And because we're looking for a universal rule that works every single time, we're not going to use specific numbers like 2 and 4. We're going to call the first point's position x1, y1, and we'll call the second point's position x2, y2. These can literally represent absolutely any 2 points in existence.
So we have our 2 points, x1, y1, and x2, y2. And obviously, there's a straight line connecting them. We just need to find the exact length of that connecting line. Let's go ahead and call this distance d. This d is our missing puzzle piece. It is literally the entire reason we're doing this exercise. If we were animating this right now in real time, d would be that glowing line just drawing itself right between our 2 points.
Section 2. The hidden triangle, a right-angled form. Now I want you to look really closely at the empty space between and around our 2 points. If you draw a horizontal line straight over from the first point, and then a vertical line straight down from the second point, boom, a shape appears. A perfect right-angled triangle is naturally forming right there on the grid, which means that straight line representing our distance d, it isn't just some random line anymore, it's perfectly acting as the hypotenuse of this newly discovered triangle.
Section 3. Base and perpendicular, measuring the sides.
So how do we actually measure the sides of this hidden triangle? Well, think about the horizontal base for a second. It just stretches horizontally across the plane. So if you take the final position on the x-axis, that's x2, and subtract the starting position, x1, you're left with the exact length of that base. The base equals x2 minus x1. Now, just apply that exact same logic to the vertical side, the perpendicular. It stretches straight up from y1 to y2. Subtracting the starting height from the final height gives us the perpendicular's length. The perpendicular equals y2 minus y1. And just like that, we've got the exact measurements of our triangle's legs.
Section 4. Enter Pythagoras, the ultimate theorem.
Now you absolutely already know this rule. The Pythagorean theorem states that in a right-angled triangle, the perpendicular squared plus the base squared equals the hypotenuse squared. Honestly, it's kind of mind-blowing that a theorem discovered thousands of years ago in ancient Greece is the exact tool we need to map a modern Cartesian grid. It's comforting, it's super familiar, and it's perfectly suited for the job. We don't need to invent some new highly complex theorem. We just need to apply this ancient, tried-and-true rule to our setup.
Section 5. The final formula, putting it all together.
All right, let's methodically walk through this substitution step by step. Step 1. We take the length of our base, which we already determined was x2 minus x1, and we plug that right into the Pythagorean theorem. Step 2. We take our perpendicular length, which is y2 minus y1, and we plug that in as well. Step 3. We substitute our unknown distance, d, in place of the hypotenuse. Watch how perfectly these pieces snap together in real time.
And here is the result of that direct substitution. We get y2 minus y1 squared plus x2 minus x1 squared equals d squared. Take a second to really look at this equation. I mean, on the surface, it looks incredibly complex, like some high-level algebra, right? But you and I know exactly what it is. It's literally just perpendicular squared plus base squared equals hypotenuse squared. Our Cartesian coordinates fit absolutely perfectly into the theorem.
But wait, we don't want d squared. We want just d, the actual distance itself. So to solve for d, we just simply take the square root of both sides.
And there you have it. D equals the square root of the whole thing, y2 minus y1 squared plus x2 minus x1 squared. We did it. This is the famous distance formula. As we've literally just proven together, this super intimidating formula is genuinely just Pythagoras in a trench coat. You never have to blindly memorize it ever again, because now you know exactly how to draw the triangle and derive it yourself.
Which brings us to our final thought for today's explainer. What other complex mathematical formulas are really just simple rules waiting to be unmasked? Today, we took a really scary-looking algebraic formula and realized it was just a basic triangle in hiding. If the distance formula is just the Pythagorean theorem wearing a mask, what other seemingly impossible concepts out there can you break down into simple logical pieces? Keep looking for those hidden triangles in everything you study. Keep asking why, and never stop unmasking the world around you. Thanks so much for joining me on this derivation, and keep on learning.